Okay, with Gaussian processes, actually, the likelihood function is actually a distribution over these possible functions here. This is the conceptual difficulty here. So you say, actually, you could imagine this as a distribution of possible functions. Right? And the prior is actually the function itself. It's a prior over the functions, over our hypothesis space about these functions. Right? And those functions, our prior, they come from a Gaussian process. Now to calculate the posterior, we have to multiply those two and calculate the posterior. And this can be done in terms of linear algebra. These are these equations. This is just shown here. Yes, it can be done. We can calculate efficiently the posterior distribution over these functions. And that's what's done normally if you just call fit in a Python code for a Gaussian process. Right? Then actually here, the posterior is calculated and the Gaussian predictive distribution using these equations. This means fit in this term for a Gaussian process. And it's the same thing we've done last time, actually multiply through. Two Gaussians multiplied is again a Gaussian. But it has a different mean, it has a different variance. And in a multivariate case, okay, this results in these matrix equations. Okay. Now the important thing is again here, our prior is a prior over functions given by this Gaussian process. And the Gaussian process is actually defined by a mean function and a covariance function. And the covariance function can be represented by a kernel function. This is what we give in. This is mainly anything we put in. Then we have data points, x and y, and we can calculate the likelihood given that prior. Multiplying those two, it's this one here, gives us the posterior distribution, the probability that this function matches the data. And that's actually what we want. Now this is already quite a lot of calculation. And now, if we want to make a prediction for data points that we haven't seen so far, we have to just plug in and make an average over these functions. This is just actually averaging out. Again, kind of calculating the most probable value for this y given the functions and the distribution over these functions. So we put in every possible function in our hypothesis space and weight actually given data points with the probability that this function happens, which is a continuous distribution over all these functions which we have selected. Right? So it selects them according to their probability. And we get out actually an estimate of how probable our prediction will be. And probably you can already open up, I've written in the solution page a notebook. I think it's exercise 3, where we can shortly have a look how this really works. In the meantime, I explain you what these kernel functions are and what is normally assumed for these kernel functions and what in what case. Okay. A kernel has to obey certain properties. For example, it should actually be symmetric, for example. And kernels can be added, they can be multiplied, and then they should still be a kernel. So we can vary also kind of kernel functions. A kernel function can also be multiplied by a scalar, and then it's still a kernel. Let's see how these kernels look like. Actually, normally, you've seen that already, I think, in the support vector machines, where we do not do a linear separation between two classes using a support vector approach. We can also use the kernel trick. Have you ever heard of that? Kernel trick? That in a support vector machine, I think you can formulate the optimization problem so that it's just a scalar product of the data points. And as soon as you have a scalar product, you can also map the scalar product to a different space. And that's the kernel trick. If you have just a scalar product, for example, two vectors, x times y. You can also calculate a phi from x times from x times a phi from y. And this is actually called the kernel trick, and by doing this, actually, you can map this space of x and y's into much higher dimensions, and you get smooth borders for your class edges. This is a trick which is also used in support vector machines, and also here it's done. Actually, we can represent it. Actually, it represents the scalar product in this data space. It's the kernel, and the kernel can be additive. So the kernel 1 plus 2 is again a kernel. It can be multiplied by a positive scalar. Any function, so x times a function, it can be separated. Function of y is again a kernel, can be a kernel. And then a product of two kernels is also a kernel. This obeys all these laws kind of a scalar product in data space. Let's look at some of these kernels. Here, for example. This is the kernel we looked at the beginning in this simple example, where we said, okay, two data points are highly correlated if they're close together. And we put actually kind of an exponential function, a Gaussian function again, for defining this correlation. So this is now a part of the multivariate covariance matrix. And we would put in here this x and y. We can tune it also by a lambda, and this lambda takes over actually the function of a variance now. But this is now called a hyperparameter because it's not directly defining the functions itself, but it's a hyperparameter. The functions actually, they're our priors, and the priors can be controlled by a hyperparameter. So this lambda is called a hyperparameter. Whenever a kernel only depends on the distance between two sample points, we call it invariant. Right? It's an invariant kernel, and that's the case here. It's only the distance that goes in, so this is an invariant kernel. It can be translated, it's transitive invariant for translation. And this gives very smooth functions, and we can actually tune the smoothness and the fineness of these functions by this hyperparameter lambda. So we can tune what kind of functions we want to have, so it gives smooth functions, but only one parameter, and this sigma squared. Zero. Yeah, probably it's now time to start this notebook. I think it's A3, right? Sampling, no, it's A4. From a Gaussian distribution. Let's have a look at this. A3, yeah. Lab 9D, plot posterior and prior. This is that one. Did you find it? Okay. Here, I just summarized the theory again, that we now sample our prior functions from this Gaussian process, and maybe what we have to define for this Gaussian process is this covariance matrix. And the covariance matrix is defined by a kernel function. It makes it easy. We don't have to define this 100 times 100 matrix. We just define a function which calculates actually the variance for each point. And we start with different covariance functions. The theory again, you can skip that. Let's start here. So, Gaussian process is already implemented actually in scikit-learn, and we use now a regression. Not a classification problem, but a regression problem. And there are already predefined kernels, for example, the radial basis function, the Martin kernel, rational quadratic. We'll go through those. I just import everything we had. To just look how this variability of the functions could look like. And this is now our expert know-how that defines which one we should take. This comes now from your experience, from your expert know-how to say, yeah, okay, we have to this FedEx course or so, we have to model like this, for example. Or a periodic function, you will see we use a sine squared function. Now, here we define just a list of possible kernels, and you can play with these hyperparameters. So every kernel has certain hyperparameters. For example, this squared exponential kernel has the lambda and the sigma 0. And we can define, okay, how much they should vary, how hard they should be correlated by using these hyperparameters here. And these are these numbers which are here given. And we go just through this list now of possible kernels. I define a Gaussian process regressor using the kernel, and the kernel is one of those in the list, which predefined parameters lambda. These hyperparameters, they have to be tuned as well, right? And then we just plot them, just to show them how they look like. And if you see this now, we have only few data points, but we have some assumption here over the data points. If we just would draw functions like that, we would get something uncorrelated like this one. This is just random sampling from a Gaussian distribution over these functions, for the radial squared distribution. But as soon as we give evidence, some data points, we know, okay, it is certain that the function must go through those points, and then it restricts all the possible outputs here in the posterior like this. And what we get is not only here this black line, but the distribution over all these possible values. And this is indicated in the gray shading here. It's plus minus a variance. So this is the probability that given those data points, and under the assumption that the data comes from a Gaussian process with this exponential square functions, then you can assign a probability that you will find a point in between here to be 68%, for example. And outside here, so it's not just an error band which is just wide, but assuming now that these points are correctly measured, you see that actually as closer as we are here to a given data point, because they're highly correlated, that the smaller also will be the error bound, because we have specified it to be actually an exponential squared covariance function, which says if they're close by, the error is also small. Now you can go through a different family here. This is the quadratic, rational quadratic. It gives different ways, or a periodic. It tries to fit a periodic function into it. This is our prior know-how. You see, okay, the bounds go down here. It's quite narrow, but it's not fully periodic. You see the flexibility that this Gaussian periodic function has. It's not just a sign that you fit into the data, but it just says it is a periodic function. But the periodicity is not fixed, because itself, this periodicity has a variance. So it's quite flexible now to fit kind of data or data functions to data points. And this is the only kernel which is now not transitory invariant. It's just a slope, a linear curve, and of course this is not invariant to translation. So this would be a standard linear fit, but now in a Bayesian view. And the Matern kernel, this is now where actually the non-smooth functions start. You have seen it before when I put the power to 1 or power to 0.1. So if we don't have just squared distances, but some absolute distances and so an L1 norm in this covariance function, it gets deep, it gets non-continuous almost. It gets a little bit rougher, and you see, okay, this could now be really kind of a rough process. The Matern kernel would probably be good to predict some shareholder values or whatever. Yeah. And here, these functions are explained a little bit. I also describe the properties, and this should help you just in practice. If you ever use these Gaussian processes to fit some data, to make predictions on given data, and this is really powerful if you only have few data points to get the best out of it without having the risk to overfit data. If you only have few data points that you have to extrapolate all these data, it's a good advice actually to use Gaussian processes. And sometimes you have to put up lookup tables which should look like kind of smooth. And then you can control the smoothness of these lookup tables because they probably have to be differentiable using Gaussian process with smooth functions like this radial basis function, the exponential squared function. So we used it many times actually to put up things into lookup tables for data we could not measure, but we knew that they will be used. And the best thing is we could do in practice is really using Gaussian processes to extrapolate the things, to even specify the uncertainty that we then predict when we have it in a machine and say, okay, we can give you a prediction, but it's quite uncertain, but we can bound this uncertainty or specify at least. So you can control actually the extrapolation. So probably it's good to go through the squared exponential kernel, two hyperparameters, sigma 0 and lambda. It's only dependent on the distance, so it's stationary kernel. It's very smooth also by the reason that it is itself infinitely many times differentiable. Then we have the rational quadratic. This is more or less just a 1 plus an x squared. It looks quite similar, like the one before. And you have another parameter, another hyperparameter. So this makes it actually 1 over 1 plus x squared. It's like a kind of called also Lorentzian function. It looks quite similar to a Gaussian, but it's called a Lorentzian function, which has a kind of a bigger tail. And you can control this tail by this hyperparameter alpha. It gives now this distribution. It's also stationary, only depends on the distance. And we have two hyperparameters to control all these functions from it. The next one is the sine squared, and it's amazing that we see, okay, it's a sine squared in an exponential to give actually the correlation between the data points. So it's quite complicated. So this is the entry of the covariance matrix of a multidimensional Gaussian distribution for a periodic function. Looks like that. And we can control it by a parameter p, which is called the periodicity. And again, actually a lambda squared, which gives actually also the variance here over this lambda squared. And periodic functions, for example, we'll see the CO2 prediction. This process, Gaussian process, was mainly pushed by Mr. Rasmussen, and he did in an early stage actually a prediction over the CO2 concentration of the development of the CO2 concentration in Hawaii, just to see how it could rise, and giving also the uncertainty about it. We'll just look at it, and how he constructed then quite a complicated kernel to say, okay, this is the variance over the season, this is the variance over longer terms, and so on. This is the noise term. We'll just see how he constructed this kernel function. This is actually more or less just a straight line fit, more or less. It's a non-stationary kernel, you see. It's not translatory invariant from x or x prime. If x prime is double the size, it will be also double the size. So it's not dependent on the distance only between x and x prime, but it's directly dependent. And that's why it goes up. The further away I go, the bigger is my uncertainty. Okay, and then we have the Motor kernel. This is this more or less almost non-continuous shaky kind of functions that you could draw from a Gaussian distribution. So it's really shaky. And yeah, you can control it also. It's only distance dependent, so it's a stationary kernel, lambda, and then you have a nu and a gamma. You have a lot of parameters here to control this shakiness of these functions. So it's mainly here now really a stochastic process for finance topics that could be used to. Okay. In summary, we can just make say that Bayes' approach is a way to put our assumptions into a prior distribution. Prior distribution is a distribution over parameters. When we have that or assume that, we can calculate by using Bayes' theorem a posterior distribution, which gives the probability that we will meet these kind of parameters. Or an update, you can also say, as soon as I have new data, I can make a better prediction of how good these parameters are and how they shift over time, for example. And by this averaging out over all possible parameters tagged on, we avoid the overfit problem. We never have a problem by overfitting because we can at any point specify the uncertainty of our prediction. It's not just say, yeah, it could be here, but it could also be here. We can assign a probability because we calculate the posterior that it is exactly here. And when you do an overfit in between two data points, you're never sure how probable, if you make an overfit in a polynomial estimation, the curve will go through there, but you never have an assignment of how probably it will be that it goes through this one. And you have to do it yourself to minimize some criterion, to add regulation, to say, okay, I have to reduce complexity that we are in this sweet spot in a learning curve, for example, that we don't have an overfit. And here this is automatically averaged out. And that's the nice thing. So no risk of overfitting. Calculating with general distributions is a hard thing and is done numerically by sampling methods. And one thing is here Monte Carlo, Markov chain Monte Carlo methods, or this no U-turn sampling. It's a special thing of a Monte Carlo sampling methods. And these two things actually are, for example, in the package PyNT3, they're integrated. So if you really have difficult things to model one, and you have difficult distributions, go for numerical methods and sampling methods using Markov chain Monte Carlo methods. That's actually more or less the summary of it. And now let's look at this. I know the data is quite old. He did it 98 or so when he also propagated Gaussian processes. He said, how will the CO2 concentration here in Mauna Loa evolve over time? And you see that the fit is quite good. It's now a Gaussian fit using a Gaussian process. But what's turned out, these parameters are actually posterior already over this distribution. So you get these parameters on. What does he take? He takes a radial basis function here, another one for the noise. Then he takes a periodic one. Where is it? Here, the x sine square, to give this seasonal variation. And a rational quadratic to make the big slope. So he says it's a sine superimposed to a slope, but then we have two kind of noises, which are distributed like that, and an additional white noise. So it's quite a complicated kernel. He puts these all together and says, this is actually what I know about, for example, from physics. We have a periodic thing, we have white noise, we have Gaussian noise, all this. Periodicity could also vary a little bit. And he puts this total kernel together. So he says k is k1 plus k2 plus k3, 4. And the whole kernel now, we put into our multivariate Gaussian distribution. We can add, and that's how you do modeling using Gaussian processes. You look at what you want to model and say, okay, what kind of functions are hidden here? With certain uncertain parameters, and we control them over the hyperparameters that can be estimated using the posterior. And now it's not that complicated anymore. It's kind of doing a curve fit, how we would do a normal curve fit and say we have to define the function once, and then we estimate, normally using a maximum likelihood approach, all these parameters. But using a Gaussian process, you don't only get the parameters out, but you also get the uncertainty and the distribution of it. And that it turns down here, you would never foresee probably. But probably it's here, and it's not only a slope here, it also turns around. and you see that the uncertainty goes up. The uncertainty also in the periodicity says that there's also jitter in the periodicity. So it's not absolutely sharp here. And over the years, it starts to smear out and get more and more uncertain. This is normally what you don't get out by a simple curve fit. Simple curve fit would just predict what's going on, and you don't have the uncertainty about the data and the parameters. So that's what you get more. Of course, it's a lot of work more, but using actually the implementation in scikit-learn, it's not that difficult. Conceptually, I think it's quite difficult to understand, okay, we define a covariance matrix of a multivariate function by these kernel functions just to define a distribution over functions. That's probably the thing you have to think about once. But I think the easiest thing is just sample from it and look at it. And it works. And the kernel function gives kind of the correlation between these data points. How they are related to each other defines how the functions look like if you sample them. Okay. This is what we've seen. Okay. So in these two last lessons, actually, I tried to bring you the idea closer what Gaussian, what Bayesian thinking actually means. In terms of, we take our assumptions, our experience, our uncertainty over the model parameters into account to get the best out of it. And it's a way actually to fuse together actually our expert knowledge and the data and let them speak. And either the data wins or the prior wins, depending on how much data I have or how consistent the data is with the prior. So I think it's the most natural way to bring both things together. And it's additionally actually a good way to say it's not only this prediction, we can also say with this significance, I can be sure that the data must be within that interval. If you have to specify kind of an uncertainty, then you get it automatically here. And third, it's a good way that you say I can continuously update and infer new know-how by adding new data. You just make another inference step by using Gaussian, the Bayesian theory. So you take new x prime or x star or y star together, calculate a new posterior. As soon as you've made new data, you make the likelihood and turn it down. And it's always like that. So you go from the prior to posterior, prior, posterior, prior. And you can do that as many times as you want, every day if you want. That's kind of a Bayesian update step. And it's the best what you can do if you have just new evidence, maybe new data. Yeah, this was our journey now through Gaussian processes and Bayesian theorem. And I would also stop here. And I would suggest probably if there's now a little bit time where we can go through together to some of the exercises probably we've not looked at yet, if you agree. Yeah? So I thought of two things. For example, one thing would be exercise number 9 from the last series, which calculates explicitly how this posterior estimate changes our prior. I've seen that I've made some typos there. They're corrected now in Moodle. Some 0 was missing and an n was missing. I corrected it now. We could go through this one if you like, or we can also once calculate this solution, and I think this is really essential. Probably you know this one, xt minus 1 xt y. Something like that. Have you ever seen that? That's the pseudo-inverse here. And one example now in the new series, 9b, is actually how do we get to that? That's the maximum likelihood solution for any linear problem. Linear means linear in the parameters. It's the Moore-Penrose inverse. And it's actually the least square solution of any linear fit in the parameter. It's very important here and it's often used. This is just the normal curve fit. We could also do that, so whatever you like. Did you ever see that one? You understand that? Shall we do it together? How we come to this solution? How a linear fit works? I think it's quite important. Huh? Or shall we first make a break, as you like? A break? Okay.